What's good, y'all? We are back talking about logical operators. In this video, we're going to talk about a third operator, which is called the logical OR operator. Let's jump right in and define what that means. The logical OR between two propositions P and Q is denoted as P vertical bar Q. That little vertical bar is also sometimes called the pipe key. We'll see where that is on the keyboard in just a second. When we see those symbols in that order, we read that as P or Q. The proposition P or Q is true exactly when at least one of the propositions P or Q is true. I also like to call this the logical inclusive OR operation. We'll talk more about the difference between inclusive ORs and exclusive ORs. In general, however, mathematicians are a bit lazy and they'll just call this OR. So remember, the whole idea is that P or Q is true when at least one of those propositions, P or Q, is true. Let's take a look at the truth table associated with this OR operation. Specifically, we see that the general form of the operation involves two component parts. It involves a proposition P and a proposition Q. Each of those component parts has two possible truth values. So P can be true or false, and Q can be true or false. In other words, there are a total of four possibilities: P false, Q false, P false, Q true, P true, Q false, P true, Q true. Remember, when we're doing the P or Q operation, we say that P or Q as a proposition is true exactly when at least one of P or Q is true. So let's take a look at each row. If P is false and Q is false, neither of those propositions is true, so P or Q is false. On the other hand, when P is false and Q is true, at least one of those propositions is true. Thus, we say that P or Q is also true. When P is true and Q is false, at least one of the propositions is true. So P or Q evaluates as true. And when we see that P is true and Q is true, one of those propositions is true, at least one. In fact, both are true. And yet we still say that P or Q is true because the definition of P or Q being true is exactly when at least one is true, although both might be true. This definition leads to the idea that this is an inclusive OR because we include the possibility that both are true. It reminds me of a joke about the mathematician that goes into an Italian restaurant. Mathematician walks into the restaurant, sits down, the waiter comes over and takes the mathematician's order and then asks, "Would you like soup or salad?" And the mathematician, she looks up at her waiter and says, "Yes." In other words, that mathematician, she's interpreting that statement soup or salad using the inclusive OR logical operation, not the exclusive OR logical operation, which business owners love, but diners might not. Let's take a look at how to type the OR operator into MATLAB. So the OR operator is denoted using the vertical bar symbol, and that performs the logical OR operation. On a keyboard, the vertical bar symbol is on the backslash key, but we actually have to hold shift in order to access it. Notice the backslash key has two symbols on it. It has the backslash and then it has the little vertical bar. I have heard that called a pipe symbol, P-I-P-E. In order to get to that vertical bar, I hold the shift key. Notice that will get me to the second functionality, and then when I push the vertical bar, I will get the exact OR operator that I want, which will allow me to do OR operations using MATLAB's logical data class. Let's get started by testing the OR operator using logical scalars. Specifically, we'll look at different rows of our truth table. Let's start with row 1, and we'll set the logical scalar P to be false. We'll also set the logical scalar Q to be false. Remember, we say that P or Q is true when at least one of those is true. In this particular line, this logical scalar is 0. The other logical scalar Q is 0, so P or Q should also be false because neither is true. So when we do P, and in this case I'm going to do shift backslash key to get that vertical bar Q, that should be logical 0 since neither one of those is true. Let's go back and we'll set P to be true and Q to be false. Notice that at least one of those is true when I type P hold the shift, go to the backslash key to get the pipe symbol, and I take P or Q. That now evaluates as 1 or true because at least one of the components was true in that specific case. Let's take a look at that last row of my truth table for a third example. So we'll say that P is true and also Q is true. Notice the reason that we called this the inclusive OR operation is because we include the possibility that when both are true, P or Q is true, because we're saying the definition of truth is when at least one of them is true. So when we test P or Q, notice that does indeed evaluate as 1. One notable comment in MATLAB is that when we're doing logical operations, we can use operator notation. So when I type P or Q, that's what we call an operator, or just a symbol that we use to carry out a specific operation. We could also use what we call function notation. For the OR operation, which is the vertical bar operator, there's also something called an OR function. So specifically, if I typed OR P comma Q, this returns the same value. Specifically, we could type help OR. Notice this is a logical OR operation identical to the vertical bar operator or the inclusive OR operator. In other words, when I'm implementing logical operations in MATLAB, I can use either operator notation or function notation. Indeed, we saw the same thing with not. So remember, P is a true operation. If I type not P, I get false. I could also type not P, which gives me false. I saw the same thing with the AND operation. Right now, P and Q are both true. When I type P and Q, I get true. I could also type and P Q, and that also gives me true. In other words, this ampersand is known as an operator. It's a symbol that allows us to do operations, whereas this is called function notation because I'm using that classic function name, open parentheses, inputs, close parentheses. These things inside are called the function inputs. When I'm using operator notation, the left and right components are known as the operands to that operator. Let's kind of level up from our examples. So far, we've been doing all logical OR operations using logical scalars. Let's use some logical vectors to do this type of work. Specifically, we'll try to recreate the truth table using the logical OR operation. We knew that P was going to be equal to a logical vector. In this case, we'll call it a column vector. So let's go ahead and type the logical function of the vector 0, 0, 1, 1. And then we'll say that Q also gets logical output. So we'll call this logical, and then we'll put in, looks like 0, 1, 0, 1. So now we've got those two vectors which store the exact information that we have. Let's check P inclusive OR Q. Notice that P or Q evaluates a true when at least one of those vectors is true. Specifically, we could do the same thing that we've seen in the previous video on the AND operation, which is to actually define a non-vector matrix whose individual entries store logical scalars that encapsulates the entirety of this truth table for the logical OR operator. So the first column of that matrix is going to be the first column of our truth table. We'll go ahead and use the column partition version of a matrix in order to store column by column. We end the first column with a comma. The second column is going to store this column of my truth table. And then the third column is going to store P inclusive OR Q. Notice this non-vector logical matrix stores the exact truth table for the P or Q operation that we wanted. For our last example in this video, let's go back to an example that we saw in our video about logical AND operations. Specifically, we had this 6x6 matrix A whose odd rows were multiples of 2, and then this 6x6 matrix B whose even columns were also specific multiples of 2. If you look on screen here, I've actually input all the code that we use to generate these matrices A and B. For a complete description of how I did this, please go back and watch that previous video. You can also try to parse that code on your own. The point of the matter, though, is when I look at A, I get the exact matrix with non-zeros along the odd numbered rows. And when I look at the matrix B, I get the corresponding non-zero columns that I desired. Similarly, LA and LB are the appropriate logical matrices which store logical ones everywhere we have non-zero values in the corresponding matrix. We can use these 6x6 logical matrices to test the logical OR operator on matrix valued input. When I type LA or LB, MATLAB is going to do an entry by entry comparison of the two matrices LA and LB. So in this case, 1 or 0, well, at least one of those entries is 1, so entry 1, 1 will be 1. Similarly, if I go down to entry 2, 1, 0 or 0, neither of those entries is 1, so entry 2, 1 of the logical OR operation will be 0. If I look at entry 3, 1, I know 1 or 0 is going to get 1. In other words, MATLAB will only assign 0 where both LA and LB have zeros, otherwise it will assign ones. So I'd imagine LA or LB is going to have all ones in row 1, all ones in row 3, all ones in row 5. Similarly, all ones in column 2, all ones in column 4, and all ones in column 6. When I go and push enter, that's exactly what I have. It's kind of like a cool looking waffle, right? I've got these little lines going across and lines going down, and the only zeros of that matrix are where both LA and LB are 0. In other words, if I were to type not LA or LB, this would give me positions where both of those things are 0. In other words, it's where LA or LB is false, those become true. Notice those are the locations where both matrices have 0. Of course, I could do the same operation using the OR function, so I could type OR input LA LB. That would give me the same logical matrix out. One fun interpretation of this logical output is an answer to the question, where does at least one of these matrices has a non-zero value? The location of these ones answer that question affirmatively. In other words, these ones mark the location where either matrix A has a non-zero, inclusive, or matrix B has a non-zero. They could both be non-zero at the same time also. We could, of course, combine logical operations to ask other interesting questions. Let's find locations where either A has non-zeros or B has 0 values. In other words, let's find LA inclusive or not LB. Remember, LB stores the locations where B is non-zero. So not LB stores the location where B is 0. When I ask this question, LA or not LB, I'm saying, where is there either a non-zero in A or a 0 in B? When I push enter, we see that the first row has all ones because A has non-zeros there. And then the second row has ones everywhere where B is 0. In other words, B is 0 in the first, third, and fifth columns. That's exactly what we see. This matrix gives me the answer where is either A non-zero or B equal to 0. The locations of the 1 affirmatively answer those positions as true. That ends the tutorial part of this video where we've checked out the logical OR operation and the corresponding OR operator in MATLAB. I actually like to call this in my own mind the inclusive OR operator because it includes the possibility that both P and Q are true versus the exclusive OR possibility where neither are true. In English, it's not clear when we use the word OR which we mean. And so I like to really say, is it an inclusive OR or an exclusive OR? The point of this, though, is that we've seen the OR operator in MATLAB works with logical scalars, logical vectors, and logical matrices. In this video, we focused on the simplest case where the left and right operands have identical dimensions. In a future video, we're going to see that doesn't have to be the case. Sometimes we can use operators on compatible sized matrices rather than identical sized matrices. For now, we're focusing on the simplest case just to get our head around what's happening. That leads us to the community challenge portion of this video. In the comment section below, post your thoughts and ideas about the following question. Why do you think mathematicians like defining OR using the inclusive OR structure? In other words, why do we find the OR operator as true exactly when at least one of them is true rather than when only one of them is true? What's the benefit of using inclusive OR versus exclusive OR as kind of the mathematical standard? You can write your ideas about that, or you can link to other people who have answered that question eloquently. In any case, I always welcome your questions and comments also in that comment section, and I thank you so much for your attention. I'll see you in the next video.